Hello, everyone. Thank you very much for connecting at such a late time in the UK and such an early time in Australia. I'm very happy to see you all here. I'll introduce myself. My name is Josep Grau-Bouvet. I'm an associate professor in the Institute for Sustainable Heritage in University College London, and I'm here today as the chair of the Heritage Science Group of the Institute of Conservation. Today, we held our annual general meeting, and as it's the custom, we pair this meeting with an exceptional talk by an exceptional speaker, and this year's speaker is Haida. Before I introduce Haida, let me give you a couple of housekeeping rules. I'm sure at this stage of remote working, we are all very familiar with Moodle, but just in case, I'll remind you of all the basics. We are on a webinar setup, which means that the main means of communication is through the Q&A function, which should be at the bottom of your screen. I hope I'm correct. Or otherwise, you press at the three buttons that say more, and you open Q&A. You can write your questions there, and I will read them aloud to Haida at the end. The presentation, we have planned for the total thing to last about an hour. So I imagine Haida is going to speak between 40 and 50 minutes, something like that, and then we'll have 10, 15 of Q&A. We have many people registered, and I see that the numbers of people are trickling in. That's fantastic. I should also say that this presentation, including the Q&A, is recorded, and then it goes into our website, where there's a brilliant collection of all the previous presentations, and indeed the number of views on those keeps increasing, and I'm glad they are being used as a useful resource. So that's everything from me. Let's introduce Haida Liang. Professor Haida Liang is a distinguished professor at Nottingham Trent, head of the Imaging and Sensing for Archaeology, Art History and Conservation Research Center, known as ISAAC. She studied physics at Sydney, followed by a PhD in astrophysics in the Australian National University. She then continued her research in astrophysics in France and at the University of Bristol before changing her research career. How fortunate we are to heritage science after a brief period at the National Gallery in London. I think I still remember the first presentation I saw from you in a SIHA conference maybe 8 years ago on tomography. Indeed, I learned what optical tomography was then. I think I remember, if I remember correctly. Maybe I'm wrong. Maybe you can correct me later. ISAAC Lab is focused on the development of non-invasive imaging, spectrography, and remote sensing instruments and data science methods for cultural heritage, research, and practice. And all this work led to the recent Queen's Anniversary Prize for Advancing Cultural Heritage Science. Very well deserved. Over to you, Haida.
Thank you, Joseph, for the introduction, and thanks, ICON, for inviting me to give this talk. And it has been a number of years since I've spoken to an audience in ICON, so I thought it's time for me to update on what we've been up to. So since at the moment there's a lot of talk about research infrastructure for heritage science, and I thought that might be a timely thing to talk about it. And plus, we just came back about a month ago from a long trip on the continent to catch up on all our ISAAC mobile lab activity that were due because of the pandemic, that we were out of action for a while. We couldn't travel. So, I just hope to report to you some latest development here. But first of all, for those of you who do not know the group very well, I just wanted to give a very brief introduction to what we do. So ISAAC is, we do two types of things. One is instrument development and method development. So in particular, data science methods lately tailored to cultural heritage research. And we also then apply these, of course, because that's the whole point of it. You don't develop instrument for not to apply. So, and that is where our interest lies as well. So we also engage application to problems in archaeology, art history, and conservation. And these are very oftentimes in collaboration with conservators and heritage scientists in museums and galleries and so on. So, and scholars who are interested in the history side of things. So here's our group, and let me just see. Sorry, I just wanted to move the icon of Joseph out of it. And the way we engage in our research is the following. So we develop instruments and the data science method in order, it's mainly in spectroscopy and imaging, and then we apply to different, the three main subjects, and also then that of course go to the end use from anything from informing conservation treatments, conservation policy, to understanding historical trade, etc. And an offshoot to that is that once we develop instruments for cultural heritage, because cultural heritage is a very unique field, and our problems with material, we deal with material science essentially, but the kind of material science we deal with is very broad, and we're also dealing with things that we don't even know whether, what an object is made of. Normally with industrial applications, we do know what they are. And it's all biological applications. You do know what tissues are, but here we don't have a clear knowledge. And so because of that, we are different. And because of the unique demands of heritage, we also develop instrument that is oftentimes quite unique. And then, strangely enough, industry and other academic disciplines somehow find us and find it's interesting, and they want to adopt our instruments. So what I wanted to say is that we often say that in heritage science, we adopt things that had developed in other fields, but oftentimes other fields can also adopt instruments and methods developed by us. And sometimes people ask, why do we build instruments and write new software and develop new methods? Because after all, some of these things are already available, in other fields, and also in commercially maybe available, you can buy. But in fact, it's not as simple as that. I've already pointed out that our problems are unique. So instruments and methods need to be tailored to cultural heritage applications. And heritage applications tend to be most challenging and demanding because we oftentimes don't know what they are. And these are made by, heritage objects made by people for artistic reasons. And so all sorts of materials we encounter. And direct transfer of technology doesn't always work, as many of you who's engaged in this would know. And commercial instruments are, they're driven by profit. If we want to develop something, they have to see whether there is a market. And heritage market is often too small to be of interest. But of course, the last Capco has shown that maybe it's not so small and funding. So but by and large, that statement is probably true. So research facilities, infrastructure need to be developed also within the community, because we are the one who use it, and we know the research question. We know what we want. And if you get somebody who's not in our field to come in and do it, it's often very difficult to get them to do exactly what you want. So you need to know about the instruments, you need to know about the research question to make that link as well. And finally, an in-house developed instrument and software is always much more versatile. And because the heritage applications are always different every time, and you always need minor adjustments sometimes. And if it is your own, it's easy. And so since we're talking about mobile lab, so just a brief intro to our mobile lab here. If you go to our website, you will see that you will see all these different categories that they're grouped into, and here's a website. You can click on it and find out about all the different techniques we have. And as Joseph mentioned, that we have been known to we've been doing optical coherence tomography for a long time, and so we have different optical coherence tomography instruments, OCT instruments here, that tailored for different applications. And we have also different types of spectral imaging, reflectance spectral imaging instruments, from close range, the ones that you're familiar with, to long range at distances of tens of meters, that in the remote sensing remote imaging category. And also we have mobile Raman spectroscopy, but not only the normal mobile Raman spectroscopy instrument, but also long range ones that can work at distances of tens of meters as well. And similarly, we have laser-induced breakdown spectroscopy that also works in close range and long range, and laser-induced fluorescence. So all these techniques, which I'm going to cover, and microphase spectrometry, and fiber optic spectroscopy of different spectral ranges, and so on, and FTIR, and including FTIR microscopy, and XRF point-based analysis and XRF scanners, and also NMR mouse, and also some of the 3D techniques, including reflectance transfer, including RTI. So we normally, I mean, I don't need to explain why we need mobile lab, because objects and in museums, it's difficult to take out, and it's easier for the instruments to go there. And also for sites, you simply cannot move it. So that's why all the instruments need to be mobile. And in fact, all the instruments we develop needs to be mobile. And that's always the case, because we are at a university, we don't have objects and so on to look at, so we have to move our instruments to museums. Okay, and all mobile lab access provided to users, if you like, or whichever way we operate in many different ways using our mobile labs. Some are funded big collaborative projects, others are user inspired. And as you will see in some of the examples I'm going to give, how that can be done. And so we go around the world as well. The furthest we've ever been is New Zealand. And so every mobile lab activity is a collaboration. It's always a collaboration. And because the people who have an interest in studying an object, they know best the research questions. And the people at the site knows best what the history of the site and what they want as well. So you can see that it happens in many different ways as the talk progresses. And the other thing is that we also realize it is important to have a DigiLab for data analysis as well, because once you collect the data, it's not a question, oftentimes it's not a question just leaving that with the user, because most situations, you need to do the data analysis as well. And so recently, through 3 different projects, 2 of them are, they all AHRC funded, 2 of them are UK-US collaborations in developing, in particular, the first one, AI for DigiLab, that is in collaboration with National Galleries, the National Archive, and the Getty Conservation Institute and Yale. We had, so we developed these, this DigiLab facility, and our collaborators tested them, and it's a joint effort to look at different case studies. And now we are offering this to the community as well. So if you have your data, you can load it in and we can help you to analyze them. And in fact, we also found that it's sometimes the best way is to combine MOLAB and DigiLab together, but that's something I'm going to go into more details of. And without further ado, I'm going to start with what I'm going to do is that I will introduce some of the newer ways of working that we are doing now, and also to give you some case studies of what we have been engaged in. So first of all, here is a remote 3D spectral imaging for large area survey. This instrument is not new. We've had, we developed that in a IPSRC project a long time ago now, but now increasingly we are using it in a systematic way, which you will see. So for example, what you have is a spectral imaging system that is in 10 bands. And why do we do that? It's because we want to do large area survey. So we so we have to make it a trade-off so that you can do this sort of thing in a timely manner. And so what we trade off is the lower spectral resolution of because in this spectral band 400 to 880 nanometers, the reflectance spectral feature is fairly smooth. You don't need to have very high spectral resolution, and 40, 50 nanometer bands are fine for majority of the materials. And so you do, and it's a filter well based system. So you collect 10 band and you get this spectral imaging cube, we call it. And so you, but the difference from a normal spectral imaging system is that it's operated remotely, and the operational range is 3 meters to 30 meters. And we aim to have high spatial resolution, and when we have this kind of system, then we have a telescope in front so that you can have the system on the ground, and you just go around. The system will just automatically scan the entire architectural interior if you wish. And the spatial resolution is something like 100 microns at 10 meters. And so we traded off between scan time and spectral resolution. That's the thing. And now what's the other nice thing is that you get for free, not only, well, the aim of spectral imaging is get a spectrum. So at a particular position, you get 10 data points. And so you get a spectrum out of it, a reflectance spectrum out of it. But for free, you also get the color image. Okay, and it's most accurate color image you can get compared to, say, for example, if you take a color camera to take image. And then the other thing you can do is to have a 3D information for free, because you will have to focus wherever you look. Once you're focused, you automatically know how far the object is by reading off the focus position. And so you get a 3D point cloud of the ceiling, for example, in this case. And so that is how we operate here with this instrument. And now we have, we realize that spectral imaging needs to be conducted in different situations. This is what I mean by you need to do some modifications. So we have a modular system where you can change the front optics, change the mode of operation to look at anything from manuscripts to wall painting, and you can even have it in the middle of the gallery and say, which painting do I want? And you don't have to reposition the instrument in front of each painting as you scan them. So, and you can go into the shortwave infrared range, which is up to 2.5 microns in wavelengths, for example, and so on. And I wanted to show you then a case study, because this is the one that we have spent years doing. And in the end, we went all the way from developing instrument and data science method to engaging in the historical research about this site. And this is the UNESCO site of Mughal Caves, and this is at the near the Gobi Desert and northwestern parts of China. And it's a site, it's a UNESCO site, and there are about nearly 700, more than 700 caves, with nearly 500 caves that are painted ceiling to wall. And so we have spent quite some time taking our instruments each summer to the site to study it, and this is where we scanned with the system the wall paintings at for this particular cave, cave 465, which is a unique painting that is of Tibetan form of Buddhism. And one of the ideas is to date the cave, this particular cave temple, and also as we collect the data, we are automatically also getting some conservation condition and information. And so what we did was that we collected a huge amount of data, because the spectral imaging device is automatic and it collects lots of image cubes. And we were able to then, so let me just go. So we would, because in order to achieve high spatial resolution, you automatically have to take lots of image cubes and mosaic them automatically. And then what we decided was, okay, so much data, what do we do? And for example, just for the east ceiling painting, that's 10 square meters, and that translates to 5,000 spectral imaging cubes or 5 billion spectra. You're not going to do it the traditional way and look at every bit of data bit by bit. So what we had to do is to employ a machine learning technique to cluster all the pixels with similar spectra together. So that in this is a cluster map, each false color represents all the pixels that have similar spectra. And by extrapolation, it's more or less correct to say that that shows a similar type of material was used at those positions as well. And then you can, so this is a composite cluster map, for example, and then you can also select one particular cluster. For example, here it shows you the drawings in here that you can extract. And so in the end, this clustering reduced 5 billion spectra to about 300 unique material spectra. And then you can focus your complementary spectroscopic analysis at the position of each cluster, so that you become more efficient. And so here is an example that we have clusters in the top area and at the bottom area of the wall, and you can say that, okay, there are these difficult to access ones at the top and the more accessible ones at the bottom. They belong to the same cluster. So if I apply all kinds of complementary technique like XRF and Raman spectroscopy and shortwave infrared reflectance spectroscopy at some of these positions, then I will be able to work out for that cluster what exactly the material is. And by extrapolation, I also know any other positions in the cave temple that belong to this cluster would be of a similar material. Okay, so that was the idea. And the other interesting thing is, by doing so, you also find information of pigment degradation. For example, we find lots of spectra, similar spectra like this, that is characteristic of platanorite. And platanorite is a degradation product of, say, of red lead. And you might miss this because they're all different colors. And, you cannot say, okay, I know that, oftentimes, you see the brownish color, that must be platinumite, but not always, because it depends on what it's mixed with. And this way actually picks them out very easily. And the other thing is that in order for us to date this, what we can do is to go to caves that have similar go to caves where we actually know the dates of them, and compare the material composition between this cave where we don't know the date and these known caves. And now you might say that in terms of pigment, say for example vermilions using old culture, that doesn't give you any information about the specific dates or culture and so on. So actually what's more interesting is a combination, how they combine the pigments to make a particular color. That tend to be much more specific and to a culture, to a period, and so on. And so we looked at these other different caves, and we were able to then compare them, and we find, for example, material similarities between certain groups of caves, and based on that we can determine that the material composition is closest to 13th to 14th century, and we were able to rule out the 9th century hypothesis. And the other interesting thing is that you can automatically process all the imaging data cubes and reveal hidden writing. Because if you have so much data, what are you going to do? You can go through all the infrared channels and try to find things. And but in this particular case, you don't see anything. And in any of the spectral channels, you see nothing. And this is a color image. By eye, you don't see anything. Yeah. But when you process it with principal component analysis, you immediately see Sanskrit writing revealed. And then what's interesting about that Sanskrit writing, it's stamped on the foot of each one of the Buddhas on the ceiling. They were found. And and this was read then by Sam Van Schack, British Library. They found that these stamped writings corresponds to a prayer, which is often used for consecration. And that's very exciting for us because that would help us to date it. And paleographic analysis shows that they were after, these are after the late 12th century. And archaeological evidence by digging in these cave sites with anything they dug out to look at some of them are writings and so on, shows that it must be before the 14th century, and also information about graffiti, etc., etc., which I won't go into. But the material analysis, as I said, was able to narrow it down to 12th to 14th century. So in combination, we were able to date this cave temple. Originally, they didn't know any time between 9th to 14th. We were able to date it down to late 12th to 13th century. That's just one example of which is also, this work actually made us realize it's not just a fashion that we need to engage in machine learning, but actually there is a real necessity when you get lots of data. Okay, now, as I said, that we are able to do spectral imaging from the ground up to look at the entire wall painting, but even if it's at tens of meters away. But unfortunately, our complementary spectroscopy techniques were only normal mobile techniques, and this inspired us to develop instruments that would these complementary techniques to long range. For example, Raman spectroscopy. Since it's laser-based, we decided that we will develop one to be able to also go to 10 meters and so on. And similarly for other spectral imaging systems like shortwave infrared hyperspectral imaging system. We also made it long range. And also, if we want, occasionally there is a need, for example, in trying to identify red dyes, you need to have higher spectral resolution. So we also have a hyperspectral version of, using a grating-based hyperspectral imaging system that is also operates remotely. So the way we work these days is that we do remote spectral imaging for large area, and then for small targeted area, we do we might do these different hyperspectral imaging from 400 nanometers to 2,500 nanometers, etc. And also all these laser-based techniques like Raman spectroscopy, we can go to long range, and also laser-induced fluorescence is similarly, we go to long range. And then we might say, well, XRF gives you elemental information. How do you do long range there? That's more tricky. So instead, we do laser-induced breakdown spectroscopy if it is allowed. Certain circumstances allowed to do it because it's micro-destructive, but the crater area is less than 1 millimeter. So in certain situations, we are allowed to perform it, and that will give us elemental information. And actually, sometimes it's much more powerful than XRF because it can give you all elements, whereas XRF can't do the light elements. So that's what we have done. So this is remote Raman spectroscopy here that we have deployed at St. Barnabas Cathedral in Nottingham. So that's the decoration was originally done by Pugin. And so we also realized working in a church, that is, you don't have curtains. So sometimes can you work during daylight? So we also devised a daylight subtraction method by modulating the laser. And so you are able to subtract the daylight and extract a Raman spectrum as you would in the dark. With obviously it will be a little bit more noisy. And so certainly that works in the UK, but we found when we went to the Alps, this doesn't work so well anymore because over here we don't have as much light, and that works okay. And the other thing is that you can do macro Raman mapping, and by doing so that, so for example, you can get a map of chrome yellow at, on this wall in the music room at Brighton Pavilion. So things like that you can do, and also you can do layer by layer identification of materials. So this is in the same cathedral as St. Barnabas Cathedral, where most of the Pugin's original decorations had been whitewashed. And one of the questions we had was that, are there still the Pugin's original decoration below the whitewash or not, before a conservation campaign can be, to clean off the whitewash can be conducted. And so we did a trial here. Well, this is showing you how it is that you can shoot with a laser to ablate a surface layer, and then you can extract the information from the next layer. So on the first layer, you would do what you normally do, non-invasive techniques and so on, such as reflectance spectroscopy, Raman spectroscopy, and then you use a laser to ablate a layer, which gives you elemental information, and then you repeat again, so you can get layer by layer information. And here is basically the elements, and the x-axis is a number of pulses. So as you go deeper and deeper, you see different elements being revealed. And in the end, we were able to then construct the stratigraphy of this. And we can also go and do remote, this is when we took the remote shortwave infrared spectral imaging system, and the remote Raman system to Fort Brokers English Heritage Site. And so here we looked at the problem with the salt at this site, and I'll show you what we managed to do here. That is, we scanned a wall using shortwave infrared hyperspectral imaging system, the remote one, so that you can do a fairly large area. And then we used our machine learning technique to produce a cluster map. And here it is for moisture, and here it is for the different salts. So you have the different false color gives you the different clusters relating to the different salt content. And so here you have a mean cluster spectrum, and for the different clusters you have. And in order to then verify what each cluster is, we use Raman spectroscopy to find out what these salts are. Shortwave infrared actually shows you, we suspect it is this salt or that salt, and then we can do Raman spectroscopy to verify, in this case, mirabolite and cyanidite. And on the top is moisture that we are seeing. And when you do Raman spectroscopy, you see calcite. So that can inform us about the salt distribution on a large area. And we apply the same sort of concept, because now the non-invasive imaging systems are much more powerful. We are able to then look at large areas of walls, wall paintings, but we can also look at a collection of manuscripts as well. And this is one that also helped us to develop further our machine learning techniques and also visualization tools to look at the data. And this is a PhD project funded by AHRC through the Midland for Cities program in collaboration with British Library to look at illuminated manuscripts from Southeast Asia. And again, we do it, we scan, there's about 60 illuminated manuscripts involved. We start with PRISM's spectral imaging survey, and then we do the machine learning aided clustering, and then we do complementary analysis. For example, here's an instrument that combines Raman and reflectance spectroscopy together, and to look at data at each cluster and also XRF. And so, for example, you can pick a cluster map. All these cluster maps are then classified or identified with a green color that is corresponds to indigo plus or pigment mix. And we also found that this is specific to Java, it seems, not any of the other islands. So that gives us information in a more organized way. And you can apply the same sort of thing, combining clustering techniques, which with a potential to scan lots of bronze objects to find out about bronze degradation problems. And so here we have looked at using shortwave infrared spectral imaging, some bronze pieces, and the aim of it is to identify the copper tree hydrochlorides that is the symptom of bronze disease. And so the clustering helps us to identify, these are the cluster maps where you find, for example, the different types of material. These are atacamite and clino-atacamite cluster, and this cluster corresponds to azurite, and that corresponds to malachite plus cuprite, for example. And so it's a quick way to pick out bronze degradation problems. And we can also do it cheaply by looking at a visible part of the spectrum as well. Once we can verify it with other techniques, then you can use the cluster maps to say, okay, this actually corresponds to Atacamite cluster, and therefore we need to pay attention. Sorry. And then I wanted to show you another aspect, that is the development we've been doing on optical coherence tomography. Just as a quick introduction for OCT. OCT allows you to look, reveal the virtual cross sections. So your instrument might be a few centimeters away from your painting, and it allows you to see into the painting and get the varnish and paint layers. So this is a 3D render of an area where there's a previous sampling done, which allowed you to do the traditional technique of seeing what the layer structure is under a microscope. And but with OCT, you can sometimes actually see better the varnish layers, because it's particularly sensitive to the discontinuity in refractive index. And so, for example, this is OCT image where this sample was collected. It's close to it to allow you to see that, and that was developed in an EPSRC AHRC combined project, joint funded project with the National Gallery and English Heritage and some industrial partners. And that was, so we had developed ultra high resolution OCT based on that, and also long wavelength OCT in at 2 microns with a laser developed by Southampton. But we have lately, we are now coming to the realization that different wavelengths of OCT gives you different information, which is complementary. And so we have, these are all the OCTs we have developed. Some of them are, okay, so these two are actually commercial devices, but the others we've developed. And you can see that at shorter wavelengths, you have higher resolution. So this gives you very fine layers. This is varnish layer, you can see. And then when you, as you go progressively to higher resolution, you can penetrate deeper, because here you have smalt on the left-hand side, yellow ochre on the right-hand side. So with the shorter wavelengths, you have better resolution and also better contrast, by the way. But you cannot see through the yellow ochre layer, whereas at a long wavelengths, 2 microns, you can actually see through the yellow ochre layer. You see the interface between yellow ochre and the substrate. So they are fully complementary, and it depends on what material you're looking at, what information you want to get at. You might use a different, whether to use a shorter wavelength OCT or longer wavelength OCT, etc. And from the very beginnings of our work with OCT applied to heritage, applied to paintings, we realized that it would be a good technique to assist with cleaning of varnish for paintings. And this is, you can, at each swab, you can see how the varnish was reduced and so on. So that gives you a more controlled way of cleaning your painting. And this was actually the cleaning done by Marika Spring at the time in 2007. And then in a recent AHRC CDP project with the National Gallery, we have developed a new instrument to really help us to do this better. Because if you look at this mosaic OCT scan of a painting, you realize that there are many layers of different degrees of transparency, and it is not always obvious to say which layer is varnish, or whether a semi-transparent layer is varnish or maybe a glaze layer. So OCT alone cannot always give you the certainty. And in fact, so we developed this instrument which combines OCT and spectral imaging. So let me show you this. So you can have, so on one hand, you have this laser that shines different wavelength light on the object, and you would be collecting then the reflected light and to give you a hyperspectral imaging cube. That's yet another way of doing spectral imaging. And so this is your spectral image, for example, of a particular area of a painting, and it's going through different wavelengths. And you can also, this is a color image of it. And then with the OCT, it is showing you the layer structure, the transparent layers. So if you wanted to know what that transparent layer is, you can do some mathematical operation to be able to extract the spectral information out. And here it is. In this case, you see the extracted extinction coefficient showing you that it is a yellow layer, and therefore it's actually most likely to be a varnish layer. Okay. So that's our new hybrid OCT microscopic hyperspectral imaging system. And we have already used it in a mobile lab campaign under IPERION MOLAB. So we represent UK with on the MOLAB facilities for the IPERION HS project. So there was this painting, The Intrigue by James Ensor from the Royal Museum of Fine Art in Antwerp, and different groups were called upon to look at this painting for a series of to address a series of research questions. And here we are. We looked at it using this hybrid instrument that shows you there is, for example, here there's two areas. This is a color image derived from hyperspectral imaging, and then there's the reflectance spectrum at these two regions. And we were wondering about this glaze layer. Is this a glaze layer or not? So OCT shows you the transparent layer, and you are able to extract the reflectance spectrum of this glaze layer. And in order to do that, of course, first of all, we have to automatically work out the thickness of this glaze layer over this small area, in order for us to then reconstruct the reflected spectrum. And similarly, with OCT, you can also see some potential soap formation, and microscopically, you can look at also the different areas of reflectance, and in this case, it's ultramarine, and OCT shows it's transparent, so it's all consistent. And so the other thing, another thing that we found very useful with OCT is to look at monitor degradation of Limoges enamel, and this is a AHRC CDP PhD project with the British Museum that's recently been completed, and we looked at over 40 Limoges enamels, and we were able to then use OCT to see. You see, OCT shows you there's delamination of the glass from the substrate. Also shows you some of some gel layer broken, and where the enamel loss, and also the air bubbles in the glass that and the structure of how it's made by doing the 3D render. But more importantly, we also found that by doing hyperspectral imaging of enamel, you are able to then find out the hydration levels by looking at the 1.9-ish, 1.9 micron air absorption line here, and work out what is called equivalent width, which is a robust measure of hydration. You can read up about that in more detail later. I guess I'm not going to go into the details here. And once you've done that, you can, because it's imaging, you can derive a hydration map here. And you can also look at normal visible part of the spectral imaging to get some clusters of material done. And you see the correlation between the material and the hydration level. There's a very good correlation, by the way, between hydration level and degradation of glass that we see with OCT. So this is a promising way of scanning glass or enamel to have some early warning signs about degradation. And so I'm just following, just show you a few other ways we've engaged with different projects. So in this case, it's an ERC project that they were looking at in the National Library of Naples, the Herculean papyri that has been charred during the volcanic eruption, and that made this papyrus look black, and we were looking at it. Our job was to see whether we can reveal different layers of writings using our OCT, and so this is something that we collected the data toward the end of September. So we will let you know what we find in due course. And so in that case, it's a scholar who has an ERC project that wanted to collaborate with us, and the object is in the National Library. So it's not just directly for the other projects of us going directly collaborating with a museum or library. And other things, it's like large format manuscript imaging, for example, as part of our From Lima to Canton and Beyond AHRC funded project. So for example, here we are in National Archives looking at spectral imaging of a 19th century Chinese military map. It's large, and so we had to scan using spectral imaging in a way to be able to do a large scan. Then we have to, because some of the maps can be quite large, and we can do a scan like this, as if we're doing it with wall paintings. And then we do the machine learning clustering, and then using our other complementary spectral imaging system to look at this. And our colleagues as National Archives would also use their in-house instruments to also do other complementary analysis as well. And then with large format, recently what we looked at is from Society of Antiquaries of London. They wanted to originally digitize a long royal chronicle, a 15th century royal chronicle of the royal genealogy roll, and we constructed this flexible wall to put it together. And we said, why do simple digitization? Let's do spectral imaging of this row. So that we have not only accurate color images, but we also have scientific material information as well. And it doesn't take much longer. So we have the PRISM system in the middle, and we just automatically scanned. And then situational reducing the barrier. I wanted to also show you how you might reduce a barrier by, going to some organizations don't have in-house scientists that works on this kind of techniques and so on, and or not have the instruments. So for example, Royal Geographic Society collection we looked at, and also Royal Botanic Gardens. This is, of course, part of the AHRC project, but it doesn't have to be. And this is where we can take our instruments down to do that. That's another way. And more recently, we went to the Alps, and in this case, it was a Swiss National Science Foundation funded project looking at the different Carolingian wall paintings in the region. And there's a group of them, and from Switzerland, from Italy, that's looking at that. And because we were going down to the region for a IPERION MOLAB activity, they invited us to do some work on it using our remote imaging systems and so on. So we did a campaign there. So there are different ways of engaging with us. And okay, so this is a quick result. So you see these Carolingian wall paintings, you don't see very much anymore, unfortunately. But after spectral imaging and PCA analysis, we can see some images of faces. And lastly, I wanted to show this example where we have our last IPERION MOLAB campaign. What was very nice was that on this occasion, we had different labs around Europe coming together, each of us with different techniques. And some of us are instrument specialists, but others are material specialists. And by working together, and also the user who applied knows about their objects, and they were doing in a European project about how to apply coating and to these World War II aircraft to protect the metals. And it's aluminum alloys that's trying to protect and see which coating works best. So it's together. And it really is very informative to have this kind of collaboration. And then I just wanted to emphasize again the importance of combining MOLAB and DigiLab to reduce barriers of access to expertise and scientific instruments. And one way to engage, this is an example of how you can engage with us. You can go to the website from ISAAC MOLAB, ISAAC Lab website to go to MOLAB, and there's a form you can fill in to engage with us, and we will see whether it's feasible or not, and whether we have the time to do it, and so on, and then you can and then we'll actually go and do it. So the DigiLab, similarly, we have this website for you to engage, and the data can be uploaded, and we will process them and give it back to you. And this is a digitization. This is a data visualization software that was developed in our last recently finished AHRC project that allows you to visualize different kind of spectral imaging. XRF, scanning is also a type of spectral imaging. Anything that has 2D spatial and 3D energy or wavelengths we call that spectral imaging. So that we can perform the machine learning clustering and so on. Okay, so that's it. I'd like to thank you for your attention, and this is a whole group that had contributed to everything I talked about.
Thanks a lot. That was very interesting. We exhausted our hour, so I won't be offended if anyone has to leave. Of course, it's very late, but perhaps we can squeeze in a couple of quick questions. There is one already in the Q&A by Ellie Caniff, who says, in what situations you would use a 10-meter spectroscopic device? In what conditions does the surrounding room need to be in?
Okay, so that's a good question. So yes, usually that is because then you have, if you are at 10 meters, let's say, if the ceiling is 10 meters, let's give an example, then the usual way of doing doing is to erect construct a scaffold and go up with your spectral imaging system, and that can be quite complicated, and it means that you can't do it whenever you want to, and so on. So I don't need to elaborate on that. So that would be the convenience that is offered. And conditions, well, as I said, that if you are in a room that hasn't got too much light, we have been at Tower of London, Byward Tower, and which has 2 windows, if I remember correctly, and there was no curtains, and we were able to do it there without any problems. And we even managed to do it in a gallery at the Nottingham Castle, where there's skylight, and that we managed to do that as well. But then, as I stress, in the UK, this is usually fine. But I think if you go to countries where there's a lot of light, as we found when we were in the Alps, it becomes more tricky. But then, as long as you wait until the late afternoon, the sun is setting or whatever, you can do it, even in those situations. But in the UK in general, we found that that's doable.
Thank you. And I hope you won't mind if I say that any further questions can be sent to you in your email.
Yes,
so
sure.
that we can close in a timely manner. But I would like to finish by thanking you again, and also by this very clear offer for collaboration. I am sure that there's going to be a lot of interest given all the work you've done already. Thank you very much, Haida. That's been super interesting.
Okay, thank you. Bye-bye.